Hello, I am Robin Magnet, and I'm going to present smooth non-rigid shape matching via effective Dirichlet energy optimization, which is a joint work with Jing Reng, Olga Sorkin-Hornung, and Max Ovsjanikov. In this work, we introduce an algorithm to promote pointwise map smoothness within the functional map pipeline. Indeed, while spectral methods display impressive performance for a wide range of settings, they are prone to fail in cases of significant non-isometry, and can result in discontinuous patches in correspondences, as seen on this image. We here display computed correspondences, using color transfer between two shapes. Our work tackles this particular issue by explicitly enforcing smoothness during pointwise map optimization. We also show that several existing methods for smoothness can be formulated as variants of each other. This allows us to incorporate them easily within the same algorithm and to compare them using a single coherent framework. Finally, we introduce a new challenging dataset with high levels of non-isometry and dense ground truth correspondences for evaluation. In this work, we leverage on the functional map framework, which has shown to be a very efficient and flexible way to obtain correspondences between non-rigid surfaces, even given some poor initialization. Instead of considering point-to-point correspondences, that is, assigning for each point on a source shape a corresponding point on the target, functional maps transfer functions from one shape to another. While this carries the same amount of information, in practice only functions lying in the spectral basis of size k of a shape are considered. The spectral basis generalizes the Fourier basis to each surface. Projecting onto this basis thus amounts to low-pass filtering of functions, and ultimately to the representation of the correspondences as well. Note that the functional map is a linear operator, and by expressing all functions and operators in a corresponding spectral basis, we obtain that functions can be represented as k-dimensional vectors, and the functional map can be represented as a k by k matrix, denoted C. K is chosen independently from the number of vertices on the original shape, and typically ranges between 20 and 100. A pointwise map can later be estimated from a functional map. A basic yet very efficient algorithm for spectral shape correspondence is a zoom-out algorithm. Zoom-out iterates the conversions between pointwise and functional maps with an increasing size of basis k. This allows to refine a potentially very approximate map into a precise one, as seen on this image. The zoom-out algorithm can be interpreted as an optimization algorithm, minimizing a specific energy, promoting functional maps associated to near isometric pointwise correspondences. Follow-up work introduced in the discrete optimization algorithm extends the zoom-out algorithm. In the discrete optimization algorithm, it was shown that it is possible to optimize a much broader set of energies, including Laplacian commutativity, bijectivity, and descriptor preservation, by using a similar iterative optimization scheme. Unfortunately, all of the energies considered in that paper are limited to the spectral domain and do not promote properties of pointwise maps. Despite their efficiency and simplicity, both zoom-out and discrete optimization suffer in the presence of non-isometric shapes and can lead to discontinuous patches in the computed correspondences, as shown on this example. Indeed, spectral methods implicitly enforce smoothness of correspondences via near isometry assumptions, which could explain the failure of these methods in such cases. In the following, we will therefore seek to overcome this limitation and directly incorporate smoothness-promoting energies within these pipelines. As we wish to obtain smooth point-to-point maps, it might be good to stop there and clarify the meaning of smoothness. In our work, we will use the standard Dirichlet energy of a map as a measure of its smoothness, where a high value of the Dirichlet energy will translate to discontinuities in correspondences. Given a function f with values in Rn, the Dirichlet energy is defined as a squared L2 norm of the gradient of f, which measures variation of f. In the case of a point-to-point correspondence pi between two manifolds M and N, we can see pi as producing vertex coordinates in R3 instead of a point in N, and its Dirichlet energy is defined again as a squared L2 norm of its gradients. In the case of discrete surfaces, it is well known that if W is a standard cotangent weight matrix, then the Dirichlet energy of a map pi is the W norm of the pullback coordinates of N, denoted pi x here. This image shows multiple correspondences between two shapes, where we additionally provide the value of the Dirichlet energy. Notice how this measure reacts to discontinuities. One issue with this measure, however, is that the Dirichlet energy is globally minimized by any constant map. This makes it an incomplete measure of map quality. It is therefore necessary to couple the Dirichlet energy with other terms, such as the one proposed in the discrete optimization framework. Our first contribution is to extend the energies considered in the discrete optimization algorithm to include the Dirichlet energy. However, as the Dirichlet energy is quadratic in the map pi, a similar approach as in discrete optimization is not directly applicable. To address this issue, we use half-quadratic splitting and introduce a new variable y, which contains the pullback coordinates. We then add an associated coupling term, which results in our final complete energy. This total energy is divided in two parts, the first one containing terms in the primal domain, and the second part terms in the dual or functional domain. Thus, unlike the previous discrete optimization approach, we now have three variables, c, pi, and y, and our approach consists in iteratively optimizing each of them while keeping the other fixed. As we demonstrate in the paper, optimizing for y reduces to a simple linear solve, while computing for pi reduces to a simple nearest neighbor search. Our solver can be thought of as an extension of the previous discrete optimization algorithm, which uses a new term expressed in the primal domain that promotes pointwise map smoothness by minimizing the associated Dirichlet energy. While the previous formulation was obtained using the Dirichlet energy, we noted that the smoothness energy term can be easily modified as long as it stays in the primal domain and that the solving procedure remains unchanged. In our paper, we show that multiple existing formulations for smoothness can be expressed as variations of the Dirichlet energy of the map and can then be incorporated in a straightforward manner within our solver. For instance, the ARAP energy introduces a new variable R and consists in three terms. First one which can be interpreted as a Dirichlet energy of the map, a second one which is a local rigidity energy, and the last one which is a coupling between the new variable y and the pointwise map. In particular, we focus on the standard ARAP and non-rigid ICP energies, as well as the ones proposed in smooth shells and reversible harmonic maps. Using consistent notations, we reformulate all energies in a coherent manner, thus highlighting similarities between them. Furthermore, by formulating these energies within a single framework, our analysis enables us to compare all these energies in a consistent way. Specifically, in our evaluation, we discard various additional regularization procedures introduced in the original works and compare the different smoothness energies using the same initialization and the same minimal regularization provided by the discrete optimization, that is, spectral bijectivity. We refer to the manuscript for a more detailed explanation of the derivations and notations used here. Evaluating this method requires challenging datasets with high levels of non-isometry across shape pairs, where standard shape matching methods fail to produce smooth maps. However, most existing shape matching benchmarks, like FOST, that include dense ground truth correspondences, are composed of near isometric shapes, and most methods obtain great results given the right initialization. This is why we introduce a new dataset called Deforming Things 4D Matching. This dataset is based on Deforming Things 4D, a synthetic dataset with nearly 2,000 animation sequences, with 31 categories of both humanoids and animals. We independently remesh each shape to avoid surfaces with identical triangulation and generate dense cross-category correspondences by manual alignment of multiple subjects. This results in 433 challenging cross-category pairs with ground truth correspondences. We evaluate our method on two benchmarks, a subset of Tosca non-isometric consisting in 95 pairs between humans and a gorilla, and the new Deforming Things 4D matching. We also provide results on standard FOST in the paper. In addition to accuracy, we evaluate bijectivity, smoothness, and coverage for each method. In the results, ours with ARAP denotes the use of ARAP energy within our solver, with similar notations for other energies. Results using original implementations can be found in the paper. We particularly highlight the standard Dirichlet energy for its simplicity and the RHM energy as it offers the best results at the cost of a higher computation time. Eventually, the selected methods outperform the baselines in terms of accuracy and smoothness, and remain competitive with the discrete optimization in terms of bijectivity. These results, however, come at the cost of a loss of coverage, as the map tends to locally collapse to remove discontinuities. Thank you for your attention.